Okay? Now what about, so it is actually multiplying by some linear transformations, right? So, the whole point is therefore, so you had this linear transformation, you wanted to solve something like this. Okay? So this has a solution, this equation, so you want it to solve. This has a solution. First, if B is not in the image, there is no solution. Right? If B is in the image, then what are all the solutions? Well, and then the solutions then obvious? Because I told you.
Can you please explain what a kernel is?
Remember, kernel, don't forget these. Kernel of f is the collection of all x so that fx is 0. Kernel and image are very, very important subspaces. Kernel of the domain, image of the codomain. And they tell everything about the linear transformation. Okay. So, if I tell you this, if B is in the image, since B is in the image, I know that there is an x naught so that fx naught is equal to B. Alright? That's the definition of the image. Right? What are the members of the image? They are precisely things which are images of some x under f, right? So if B is in the image, then it is obviously some fx naught. Okay? So now I am saying fx shall be equal to B, because if you tell me fx is equal to B and you told me fx naught is also equal to B, then fx minus fx naught is equal to 0. But linearity tells me f of x minus x naught is 0.
So doesn't make x and x naught to be equal?
No, I didn't say so. I said that, see what I'm saying. Fx is equal to b. This is same as f of x naught. So this means that f of x minus of f of x naught is equal to 0. Right? But then this means, by linearity, this means f of x minus x naught is 0.
Oh.
So this means from the definition of the kernel that x minus x naught is in kernel of f. Conversely, if you take x minus x naught to be in kernel of f, then f of x minus x naught is 0. And what is x? F of x is f of x minus x naught plus x naught. So it is f of x minus x naught plus f of x naught. So which means it is b. Right? So this shows that fx will be b if and only if x minus x naught is in the kernel. So that means x is equal to x naught plus k for some k in the kernel of f. Right? That's exactly. If k is in the kernel, then x minus x naught. So that's what you say. Right? So that's, now you see, we have a very, very quick way to tell all about linear equations. Why? So for this linear equation, what do I do? How to solve it? Well, so how to solve this linear equation? What are the solutions? First I ask whether B is in the image of F. The answer to this being yes, tells us that I have to find an x naught such that and then I have to find the kernel of f. And if the answer is no, then I stop. There is no solution. And here I find all the solutions. So I have to find the kernel of f. And I have to find a particular solution. This x naught is often called a particular solution. Now, let's come back to its matrix equivalent. If I have the matrix for F, if I tell you that A is the matrix of F, then when I'm not writing, suppose I have a base, suppose I have a basis, okay? When I'm saying that this is, then fx is nothing else but given by this. So I'm saying now I have to find x, okay, such that solving this linear system of equations, this has a solution. Now I am trying to say, what do I mean? So I have to find an algorithm for this. Okay? I have to find an algorithm for this. So what do? I use my experience. I saw that the moment I write things in the reduced echelon form, things become very simple. Now, how does it help over here? Well, reducing this means I'll multiply this by invertible matrices on the left. Okay? So Ax is equal to P if and only if okay? Remember, What was A red? Remember, it was obtained by multiplying by certain invertible matrices on the left. So when you multiply by an invertible matrix on the left, you multiply on the invertible matrix also over here, right? And so on. So that's the B red. Okay? Clear? And now, from here, it's quite easy to read whether B red is in the range or not. Okay? From here, it is easy to find the kernel of A, which is nothing else but the kernel of A red, and the image A, which is nothing else but B. Okay? So the moment we find this, our problem is completely satisfied. Completely done. On the level of transformations, it means therefore that you are not changing actually F or B. What you are changing is the basis. Okay? So the coordinates of the basis of B change completely. So in the new coordinates, B has a much more simpler form from which we can immediately see whether Fx equals to B has a solution or not. Okay? So this is the whole story. Okay? Now, how do I extend this? Suppose I have I already indicated, therefore, what should be my algorithm. Herein comes the augmented matrix. Before I go to this, herein comes the augmented matrix. Why? So what it means is, I take A, and I go by to reduce this completely. So I use row operations completely on this. Okay? But the row operations would end with A. I don't carry on with the leading entry on B. Okay? So by row operations on A, I finally obtain this. Okay? Now, if corresponding to a row of zeros in A red, you have a non-zero entry over here, then it doesn't have any solution, it doesn't belong to the image, right? So if corresponding, why am I corresponding to a zero row B has non-zero entry, then no solutions. Okay? It is exactly one solution when the kernel is only zero. Right? That means it's when the kernel is only zero, that means you know its rank is same as the number of columns. Right? So, and otherwise, it has solutions. And the unique solution rank of A, or all the columns A are independent. Yeah? If those are independent, then it is an injective map, and then if and only. Okay? Kernel is there. That's the whole algorithm. Clear?
Yeah.
Now, suppose we have two systems of linear equations. Yeah? You can extend this. So simultaneously, does it have a solution? So the first one is it's already a system of linear equations in m variables and whatever. You have another system. Okay? So you are seeing whether this full system, this total system, has a solution. How do you do it? Well, you do the Gauss-Jordan again, but this time these two. The pasting, yes, you go on pasting. And then, because suppose if this A is an n cross n, okay? N cross 1. So there are two things that is simultaneously solving. So you need a vector like this, right? It is n cross 2, which gives your answer as the first column being B1 and the second column being B2. Okay? How to solve this? Well, take this augmented matrix, apply Gauss-Jordan again and again and again. No solution for one of them means no solution for the whole system. Okay? So it has to have solution for each one of them. And then you will be able to find the general solution for X. Okay? So B1 and B2 both must be in the image to have a solution.
Yeah, this is just question to ask that every matrix can be reduced to what is shown above. I'm here and this is the question.
You are confusing with the augmented matrix.
No, I'm thinking with the answer of saying that every can be reduced to a version above. What happens if you have all that are lemons?
All the rows are 0. Oh, what happens?
No, if the whole are elements equal J, the stress is the same and the elements equal of allowance.
Okay, good. Good. So here is the situation.
In this case, what happens if that having the version to work with?
This is not rotational, but you see,
in that case, that theorem that you would I'm doing it how that now continue
okay? All right. So you see, this is the whole story of working with matrices. That's it. But you see, it has a very, very strong influence of the notions and ideas from linear transformations which we developed earlier, and you saw how quick the computation becomes. Otherwise, you will have to go on computing series after series, and you have to always look into. Okay? Alright. So it is already past my time. We have 1 more hour, and we will meet after 10 more minutes. Okay? Obviously, those who will want to run may run. Okay? What is it?
No, we have to walk, and there are no transport until we get here. So you have to walk.
Sometimes when it's 6 o'clock, you can't get a transport, that's the problem.
Oh,
Yeah,
sorry.
So does it mean that the lesson that you're supposed to do today, you do it next week?
Yeah.
Actually, it's not simple. Not that fair.
The grant was not as a gift, the grant.
No, this is not yet PhD, this is still foundation. I'm the real name. You are thinking of competition now. I changed completely. I should have taken
Which one?
Yeah,
Which one did you pass the second?
It's lineology.
Second year. What are you doing again? Get credit for it when you're perfect. That's nice.
I didn't apply for credit.
I did it twice. I take it. Get credit. That's very good. I did it twice. I did it, yeah. It was it just had a lot. No, I tried.
No, I mean here.
Yeah, I was saying later, but I didn't have it. Get your credit, this thing is not easy. So, like, what happens in the next part? You ask questions. Oh, he asked questions. Oh, the others, the ones they ask questions.
From the assignment, you see the guys, they look for takes and then.
Oh, okay.
You can if you want. But how far are you with the assignment then? Are you leaving?
I just started with the
So you are just like me first. I'm just saying.
but some of the when they
Look, so, I spoke with the guys uploading the videos. So, I'm going to
So, excuse me. Who is this guy in PTA? Excuse me. PTA, Pretoria. Pretoria. Pretoria.
Hello. Hi.
Hi. I'm sorry,
Hi.
what's your name?
My name.
Yeah.
Tepo.
Tepo, all
Yes.
you do is can you please take my number?
Okay. Yeah.
My WhatsApp number is 060 387 4246.
Okay. 060-387-4246.
Yeah.
All right. Sure. Thanks.
Thank you.
Okay. Bye.
Yeah. No,
Yeah.
I think that if I did
Yeah, it's application.
nobody is like it.
Yeah, I think these guys from the the effect of this thing.
Yeah. But maybe it's because of we shouldn't be, I don't know, because I'm now from Pretoria. Everybody is crying.
Right?
We even tried, we had a group, WhatsApp group. I was looking at their, okay, today is the strike, but nobody has a clue.
This is the start.
Yeah, you can take. What is number?
This is the start.
This number?
I think so.
Next week you coming back.
Yeah, I have to come.
I'll let you. You're just like me. That's why tomorrow I come and just take the continuous order for the just.
Oh, yeah.
Chavis is here.
Yeah, this one.
No, that's the number. Not Chavis or Chavo. That's the number. Office number is 471 375
You can just go to the
Yes.
This is his number. It's around. I don't know.
It's recorded. Right?
security company.
The problem with this module is that
It's here, it's recorded. It's always recorded.
it's coming here, will come here. So when the lecturer is there, he's always there. So switch off.
This is his department.
Yeah, if you continue now.
Yeah, ask him. Yeah, they have made
Come on, man.
they have made these videos. After I do the sum, then
That's it for that's what.
yeah, it takes.
It's for 078-804-0184.
Okay, thanks.
The thing about this module is that this guy works on is totally different.
Yeah.
On which is 1503. It was
Yes, that's all right.
action.
Putar tayo magkapatid. Oo naman, di ko pa kung download na video, di ko may sticky niya. Naging sarwa ka, and lagi na lecture na. Yeah.
Sabi ko, Sabo, I gonna be in tomorrow.
Okay. So let's resume.
The book, so what I'm going to say,
the book which is very close, the sentence also let us review. The book which is very close to the approach here which I am following is and there is an e-book of this, e-copy of this book, and the link for that I think I put in the.
I think it's yellow in the cover.
I don't remember the cover, but I put it in the.
It's a 10th edition.
It's an e-book in the UNISA library.
What is the one? I couldn't get that.
Okay? All right. Questions? I think it's the 3rd edition. 3rd, right? Yeah.
If I can use this book, I can pass.
This is the one which is closest to the approach that I am following. Yes. The only difference is that Axler uses complex numbers as his scalars, but until and unless we come to eigenvalues and eigenvectors, the story remains the same. Yes, the story remains the same. It's only from eigenvalues and eigenvectors that the story starts to deviate. The story in complex vector spaces is much, much clearer. In real vector spaces, it is a much more hazy thing. We'll see it next time. It's a peculiarity of the complex field. Okay?
Okay, so the next.
Yeah, Sheldon Axler.
Yes.
We're having your uniform.
Yeah.
Yes, downloaded it.
Yeah.
Why don't you
Because send to us.
I'll show you.
Okay. Let's rejoin with questions.
Sir?
Yes?
The textbook says that null A is implicit. I'm unsure of what that means.
Which one?
They say that null A is defined implicitly.
Textbook means where?
Oh, I'm using the textbook by David Lay.
Oh. In which connection?
Okay, the whole paragraph says that there is no obvious relation between vectors in null A and the entries in A. We say that null A is defined implicitly because it is defined by a condition that must be checked.
I don't understand this.
I also don't, sir.
Null A is what I say the kernel. So when A is a matrix, so this is one of the reasons why I avoid these textbooks. Because they just create confusion. Just for a moment, since you are logged on, you are in UNISA, you will have this facility. You go to this website This is a free service given by, well, it's free for you because you are in UNISA. You can go to this website, check the name, by name of the author, by title of the journal, paper, or the book, and when you see, it will give you a review result. Now this review, people publish and review, it is being reviewed by mathematicians throughout the world who are quite acclaimed, and this review is published. So if something doesn't have a review entry, it means it may not be authentic. Having a review entry is a plus point, and having a review, going through the review is also a much more plus point. Having a good review means that the work is really good. You should look into the review for Axler's book.
Okay, sir.
But all these other books don't have a review. So they are not reviewed by AMS. And anything which is not reviewed by AMS, well, it shouldn't be considered to be authentic as far as the mathematics is concerned.
Okay, sir.
So that is one of the reasons why I don't like these books. Now, whenever you are giving me a matrix A, we have seen just now that it tells us that you are giving me a linear transformation from Rn to Rm. It takes a member X to AX. Now the null, what is called as null in several cases, I call it the kernel. I still write as kernel of A, because that is determining. People also write it as null of A. And what I write as image of A, people sometimes call it the range of A. Okay? Now, what is null of A? Well, null of A is the kernel of A, and what is the kernel of A? It is the collection of all those x's such that AX is equal to 0. In other words, the solutions of the homogeneous system of linear equations. Right? It's a vector space, the vector subspace, right? And the dimension is the nullity. Okay? So I don't understand what the book means by saying that it is defined implicitly. But that's the null of it.
Thank you, sir. It says, okay, another sentence is, every linear combination of U, V, and W is an element of null A. Thus, U, V, W, in curly brackets, is a spanning set for null A. I don't think I understand what that means.
So
if I say something, sorry.
Yeah, continue.
If I say something is a linear combination of U, V, and W, it means that it would mean that if I had weights, right, and let's say our weights are C1, C2, and C3 with U, V, W, it would equal Y, right?
Yes. So what it says is That means you are looking into the span of UVW. Okay? You're looking into this span. Now if you tell me that every member of the span is in the kernel. So this statement actually means A times this is alpha times AU plus beta times AV plus gamma times AW, right? Now you're telling me for all choices of alpha, beta and gamma, this is 0. So in particular, you're telling me U is in kernel because you take beta and gamma to be 0 and alpha to be 1. That's 0. So by the same logic, you are telling me V is in kernel and W also is in kernel. So just saying that every linear combination of U, V and W gives me a member of the kernel just tells me one side of the story. But there must be another way, another sentence to say that if I take any vector P from the kernel of it, then P is a linear combination of U, V and W. If I don't say this, if I can prove this, then I will have that the span of UVW is nothing else but the kernel of A. Okay? So saying that the kernel is equal to this is firstly every linear combination of UVW is in kernel of A. So to show that, it's enough to show that AU is 0, AV is 0, and AW is 0. Then every linear combination would be 0. Okay? But that doesn't tell me that the span of this is whole of the kernel of A. It says only one side. For the other side, I have to show if I take AP is equal to 0, then I can find scalars U, alpha, beta and gamma such that P is equal to alpha U plus beta V plus gamma W. Okay? If I can tell both of these, then I can say that kernel of A is span of UVW. Okay? Clear?
A little bit, sir. I think I must just go home and think about it a little bit more.
Okay. Next.
Sir?
Yep.
The geometric meaning of an independent, like if we say that a set is independent, right? The geometric meaning of that would mean that the vectors only intersect through the origin. And they lie on the same plane or on the same line.
They don't lie on the same line.
If the
If they lie on the
Yes, sir?
If they lie on the same line, they are already dependent.
Oh. So then
So
how
they
can
don't-
vectors be independent in R2 because then they can't form a plane.
Wait. Here is one vector in R2. This is my origin. And here is another vector in R2. Okay? So, since you have two vectors in R2, which are not collinear, they are independent.
Oh, okay, that makes sense. So it just means that the vectors are in the same plane, but they pass through the origin.
Every vector in R2 is in the same plane.
Okay, if the vector was in R3.
Yes.
And they were
So
independent.
Now the question is a little more difficult. So you cannot find. So they are firstly like this, and moreover, you cannot find any plane which is common to both of them. Now, we have not come up with this principle till now. The method in R3, if we are in R3, what we can do is, we can try and find out, in R3, we can try and find out if they were on the same plane. What is the meaning of a plane in R3? Well, in R3, if you take a plane like this, it means that there is a vector which is orthogonal to everyone in the plane. Okay? Each plane is completely determined. Plane in R3, I should say. Each plane in R3 So, that's how we come upon with the definition, with the equation of a plane. So, suppose you give me a vector in R3. I want to find all the vectors x such that u is orthogonal to x, which we will see after two more classes. This is the same thing as okay? So, that's we often say that u1, u2, u3, or this vector u, this is often called, u1, u2, u3 are often called the direction cosines of the plane. That means the angle that it kind of measures the angle that the plane makes with the x-axis, y-axis, and z-axis. This exactly becomes the angle when I assume u is actually equals to 1. Okay, that means u squared plus, this means that u squared plus, sorry, this is equal to 1. We will see this when we do inner products and so on and so forth. So, the equation of the plane is completely determined by a single vector, and that is the normal. We call that to be the normal vector. The vector normal to the plane or orthogonal to the plane.
So, sir?
Yep.
If I say two in what's this thing called? In R3, in 3D space, how can two vectors be parallel then?
Two vectors are parallel provided so vectors A and B you want to say that these are parallel, right? We often write it in this way. A is parallel to B. And the way this happens is actually what happens is you will have a kind of a translate of them. So I'm trying to see how can I do it without using actually this notion of parallel, this notion of orthogonal. These are parallel is if A is lambda times B, that's obviously one way to say it. If you can find scalar lambda, which you have this, or in other words, A1 by B1 is equal to A2 by B2, and that is that common. So if the ratios are same, then obviously they are, we can say that they are parallel. That's exactly the meaning of saying it's parallel.
I think that explains it.
Okay. Next,
Both of them.
Yes? Next question.
Sir?
Yes?
The thing says, let H be a subspace of a vector space V. An index set of vectors B, B1 up to Bp in V is a basis for H if B is linearly independent set, and the second point says that the subspace spanned by B coincides with H. What does that look like geometrically? Do they mean that, like, if this was in R3, that H and B would be the exact same plane through the origin?
Yeah, the geometric interpretation of this is that in R3, for instance, if you have, say, these two vectors, and if you select the plane which is kind of passing through these vectors, let me see if I can make it lighter. Something like this. So if you can find the plane passing through these, okay, this plane, yeah? So that is the subspace H. This is the subspace H. So it didn't come up. This is the subspace H. Okay? So your vector, so in R3 it means that H is the subspace generated by those two, means it is the plane which is, that means you take the vector which is orthogonal to both of them, and that gives completely determines this subspace H, this plane H. But if you are in higher dimensions, well, we cannot think of it anymore. I mean to say, we cannot visualize it anymore, but that's where the algebra helps us out. We cannot visualize it, but we say that, okay, we have this list of vectors. This is a linearly independent list of vectors. And H is the span of this. So that means what is H? Here?
So is the, what's the squiggly line called?
This one?
Yes.
That is the Greek letter xi.
Xi.
You can use any abbreviation.
So I'm sorry for asking so many questions.
So it's fine. You're welcome to ask.
Okay, another question of mine is that, okay, so we have a set called sin t cos t, right? And then they said sin t and cos t are multiples of each other. Okay, so then I understood why they said that they don't intersect when t lies between 0 and 1. They would be...
What did you say?
There's a set sin t and cos t.
The pair. Is this pair?
Yes.
Okay. And t?
And t lies between 0 and 1.
Okay.
And then they said when t lies between 0 and 1, cos t and sin t aren't multiples of each other as vectors in 0, 1 with those brackets. So I was actually very confused with this whole question. It was an example. I don't think... So are sin t and cos t linearly independent or linearly dependent?
It is definitely, the question of linearity doesn't arise. These are not linearly independent, these are not linearly dependent. If alpha times sin t plus, now I don't understand what you're saying, plus beta times cos t is equal to 0.
Yeah. Okay, let's say t is equals to pi over 4, right? Then sin t is equals to cos t, and alpha is equals to 1, and beta is equals to -1. Our answer would be 0, which would mean that a solution other than the trivial solution exists, which makes it linearly dependent.
Wait. Sine of pi by 4 is a real number. Cos of pi by 4 is a real number. And any two real numbers are linearly dependent. You take any real number p and another real number q. If p is not equal to 0, take lambda to be q by p. Then I know that q is lambda times p. What's the new thing in it? Any two, and that has to be because R1 is a one-dimensional vector space, so any more than one vector, that is any more than one real number, will be a linearly dependent list. So that is nothing.
Okay, but sir, let's say t doesn't lie between 0 and 1, right?
If you fix any value of t, wait.
When sin pi over 4 is equal to cos pi over 4.
Yes, it might be. That's a special case when your lambda is 1.
Yes, and your beta is -1. That would make the trivial solution possible.
Yes,
using
but wait. If you take any t, not only t between, if you take any t in real, Now if you look into this list, sin t and cos t, okay?
Yes,
Then
sir.
this list is a list of two numbers and hence linearly dependent.
What?
It's linearly dependent in R. This list is linearly dependent in R. So the question is, where are you speaking?
Oh, yes. I understand. Yes,
So
sir.
I think the question is not clear.
Yeah, I also think so. Thank you, sir.
Thank you. Any further questions from other centers or any further questions? If not, then let us disperse. Our next lecture will be on Tuesday.
Sir, I have one last question.
Yes.
Okay, we have a theorem that says that an indexed set V1 up to Vp of two or more vectors such that V1 is not equal to the zero vector is linearly dependent if and only if some Vj with j is greater than 1 is a linear combination of the preceding vectors.
Yes.
But I'm confused. Why does it specifically...
Wait. So you have this list of vectors. So let's first do a specific example. Say I have a list of 10 vectors. How do I decide whether this list is a linearly dependent or a linearly independent list? So, first step, I check whether V1 is 0 or not. If the answer is yes, then it's a linearly dependent list.
So what happens if V2 is 0?
Wait, I'm coming. So if the answer is no, I know that 1 is not equal to 10, so I then go to the question if V2 is 0. Yes, linearly dependent. No, then I ask, is V2 some lambda times V1? The answer is yes, linearly dependent. No, I go to V3. Yes, linearly dependent. No, well, then I ask whether V3 is lambda times V1 plus mu times V2. Yes, linearly dependent. No, go to V4 and so on. So, you carry on and on and on.
Until you
If
get
at some stage it becomes yes, so the answer is linearly dependent. No means what? See, what have I done over here? I'm checking whether V3, so this is the same thing as asking whether V3 is in the linear span of V1 and V2. This is the same thing as asking V2 is in the linear span of V1. So, what is the story then? When do we have an yes? So we have the answer yes in the only case that there exists a K such that either Vk is equal to 0 or Vk is a linear span okay?
Yes,
So that's my proposal. So B is linearly dependent. So the answer to yes means linearly dependent, right?
Yes, sir.
So yes means B is linearly, so this actually means linearly dependent. So that's the proposal, that a list of vectors, there's nothing special with 10, you can do it with any n. Okay, so here it will be any n. So the list, therefore, a list of vectors is linearly dependent if and only if there exists a k between 1 and n, so that either Vk is 0 or Vk is a linear combination of the previous ones. That's
Yes,
it.
sir.
If it is
I want to know why is it specifically the preceding vectors? Like what happens if, like for instance, V3 is a linear combination of V5 and V10?
good. So you are saying V3 is in the linear combination
Of V5
V5
and V10.
and V10, right?
And V5 and V10 aren't preceding vectors. Does it specifically have to be preceding vectors?
Wait. So therefore, this can be true even only if V10 is in the linear span
of V5 and V3.
Get it?
Okay, sir. I see.
And this is obviously smaller than so there it is. And this is even smaller than so it doesn't actually contradict what I am saying. But yes, you are right. If you immediately can come up with this, if you can immediately by looking into the thing, if you can immediately come up with such a relation, you don't have to check for all these cases, you know. But in general, what I was suggesting is this procedure provides an algorithm to check whether any general list is linearly dependent or linearly independent.
Thank you, sir.
Yep.
Thank you, sir.
Thank you.
Bye, sir.
Bye.
So when do we meet? Oh.
That means 19th.
Answer the time.
As far as I remember, it is still the same.
It's 47. It was 47.